Here we have the graph of our function again, and I want to chop it up again, but I want to chop it up in a different way this time. This time I want to chop it up into intervals according to how the function is bending. You see, this is about 0.8, negative 0.8. And to the left of that negative 0.8, we can see that this is kind of bending up, right? If you think of it as like a cup, it could hold water, right? For the purple region, it's between about negative 0.8 and about 1.5-ish. It's bending down, right? This wouldn't hold any liquid. And then again, to the right of about 1.5, the green portion, we're bending up again. The way it's bending is called concavity. And in the blue region, we would say that the graph is concave up. In the purple region, we would say it's concave down. And then in the green region, again, we would say it's concave up. Now this is going to get a little bit weird, but try to follow me here. If we move from negative infinity, or that direction, toward negative 0.8 in that blue region, and if we picture tangent lines, then we can see that they're getting shallower and shallower until eventually they become 0. And look, the slope of a tangent line up here is going to be very negative, and it's getting less negative. Getting less negative means getting bigger. And so here we would say that f prime is increasing, right? The size of the derivatives is getting bigger. In the purple region, we see that f prime is positive there, and then it approaches 0, and then it goes negative. And it's pretty clear, I think, to see that f prime is decreasing. The slopes are becoming more and more negative. And so the derivative is getting smaller in value. And then for the green portion, the derivative, or the slope, starts out at, for that tangent line, is negative, less negative, 0, positive, getting more positive. It's increasing, right? So here we would say f prime is increasing. Now let's go back to what we saw before. I'm just going to ask you to hang on here. When f was increasing, we said f prime, when f was decreasing, we said that f prime was negative. When f prime is decreasing, we will say that f double prime is negative. Stick with me. Let's go back. When f prime is positive, then f is increasing, right? So here, if f prime is increasing, then f double prime is positive. So that happens in both the blue and the green regions. Before we give a label to this whole situation, let's take a look at these derivatives again, or these tangent lines again. In the blue region here, notice the tangent lines are all below the graph itself. In the purple region, the tangent lines are all on top of or above the graph. And in the green region, where again, we've got, that the tangent lines are below the graph. The vocabulary here is concave upward or concave downward. If the graph of f lies above all of its tangents on an interval, that's over here and over the blue region and the green region, then f is called concave upward on the interval. And you can see that's like where it bends up, and it would basically hold liquid if it were a physical object. If the graph of f lies below all of its tangents, so here's the graph, the tangents are above it, then f is called concave downward. Now concavity is related to the sign of the second derivative in the following way. If f double prime is positive on an interval, then the graph is concave up. If f double prime is negative on an interval, then the graph is concave down. So the second derivative will tell me how the graph is bending. One more piece of vocabulary here. An inflection point is a point on a curve if at that point the curve changes from concave upward to downward or from concave downward to upward. And so where the blue and the purple meet, we have an inflection point. And where the purple and the green meet, we have another inflection point. to find out where an inflection point is, look, if the second derivative was negative to the left and positive to the right, then at the inflection point, f double prime is equal to 0. But right now, I gotta say, f double prime equaling 0 doesn't always mean we have an inflection point. Let's again think about y equals x cubed. No, that one won't do it. Let's think about y equals x to the 4th power. The derivative is y equals 4x cubed. The second derivative is y double prime equals 12x squared. We know that this is 0 when x is equal to 0, but to the left of 0, our graph is concave up, and to the right of 0, our graph is again concave up. And so just knowing that the second derivative is 0 doesn't automatically mean we have an inflection point. And I got to say something even further here. Let's consider the graph of the cube root of x. So y equals the cube root of x. We can see that to the left of the origin, the graph is concave up. To the right of the origin, the graph is concave down. If we take a derivative, though, y prime is equal to 1 over 3x to the 2/3. Y double prime is negative 2 over 9x to the 5/3. Y double prime does not exist when x is 0. But since concavity switches from concave up to concave down, 0, 0 is an inflection point. All right, so how can concavity tell us anything about local extrema? I'm glad you asked. Here in the blue region, we are concave up. You can see we have a local minimum, and there's also a local minimum in the green region where the graph is concave up. That local minimum is at a critical number where the first derivative is 0. And then in the purple region where the graph is concave down, we have a local maximum. Again, the derivative is equal to 0. So what we're seeing is if I have a critical number, and at that critical number, the graph is concave up, I'm going to have a local minimum. If I have a critical number and at that critical number, the graph is concave down, I have a local maximum. This is summarized in something called the second derivative test. Suppose f double prime is continuous near C. If f prime is equal to C, critical number, and f double prime is positive, then f has a local minimum at C. Remember, f double prime being positive is concave up. If you can picture that, then you can picture the local minimum, right? And then if f prime equals C, so I have a critical number, and f double prime is negative, now that's concave down, then f has a local maximum at C.